let's jump right into it. One of the nice things about dspy is that you can just say hello like that. And this is how you would call an AI and get an answer. This is simple. There is no boilerplate. There is no JSON to construct. This is it. Then the really powerful thing about dspy is this right here. And so we will do an AI program. In this case, we will do a RAG. Okay, so retrieval augmented generation. And so our RAG, we will want to do it where our model uses chain of thought. So we specify it here, just like that. And so how would we define a RAG program? Well, a RAG program has context, question, and an answer. I don't think we can say it in shorter than that. And so let's just do this here. Context, question, answer. And that's it. We just made a RAG program with dspy. Now I can call it. And so if I set some context, let's just have something simple like, it's 4 o'clock. And let's have a question like, what time is it? And let's run it. And so now the call is going to OpenAI. The GPT 4.1 Nano is reasoning through the response, and it's giving us the response. If we had saved that response into a variable, what we receive is what they call a prediction object. And so when we run that, we can access the answer just like this here. And so I just don't know how you can do that in a more, I'll call it Zen. Like, I don't know how you can do it nicer than that. It's really nice. Then I can already hear you. Yes, but I need to say this, I need to say that, my prompt, how do I say it that if you're not performing, your grandmother will go to jail or whatever? Well, you don't, because dspy will do the optimization of the prompt just for you. We will go through all of that in this video, but let's now take a moment to understand the two code chunks we had at the beginning. So the first one is a very obvious one to anybody that has ever programmed in Python. We just import dspy. Okay, that's simple. Second one is quite interesting. There's quite a bit happening here. In this first part here, we are kind of setting up our backend. We're setting up what we will be calling. They're using a library called lite LLM. And this is important to know because if you want to know, oh, can I call this new provider or this new tool, or can I self-host and call my own LLM with VLLM or SJLang or Max or all those tools, and you really want to get into the details of how to do that, well, you would rather go read the lite LLM documentation than the dspy documentation. In general, lite LLM really supports everything. The answer to the question, can I call X, Y, Z, is usually yes. By simply changing the string here and saying that we want to call Gemini, it will change it to Gemini. So one thing that you may be surprised that you don't see right now is that you don't see an API key. This is because I have set it on my system. And so I don't need to give it to all of my programs. They are just going to pick it up, because also lite LLM follows a nice standard on how you should name your key in your terminal environment so that they go pick it up automatically for you. This first line is this. You just change this here and basically you call any LLMs you want. This is pretty simple. It's really nice. Second line is configure. Configures your language model for the whole program or for the Python session. You can call it multiple times as you're scripting or as you're running the code, and every time you call it, it's configuring. It changes the configuration for whatever you're doing. And so if I do it like that, that would mean that even though I'm defining two LM, the one LM that will be used will be this one. Although this here is a direct call, so it's a little different. I'm just deciding directly what to call. Oh, this is interesting. You've seen how fast this is. This is because dspy, with the help of lite LLM, caches your prompt. So if you're sending exactly the same prompt to exactly the same model, it was cached in the memory of Python of this current session. And so it won't recall the provider. And so you won't repay for those tokens. You can change that. You can set cache equal false if you want. And so then if you do cache equal false, you will see here that we will be waiting for a little longer here. It's because now it's calling, okay? The other way that you can specify what language model should be used for this call is using this with dspy.context, lm equal your model. So in this case here, I will be using Gemini for this RAG, whereas for the rest of my program, because I configured LM GPT-4.1, it would be GPT-4.1 Nano that is used. That's it, okay? This is also very nice. The reason you should use that and why we are not passing the variable directly to RAG or these sorts of things, it's because dspy gives us a lot of tools to call multiple LLMs in multiple requests at once, asynchronously. And this is the way that we can do it while being thread safe. I feel we're not good with the introduction. Let's move to make another program. So what this program will do is that we will give it a picture and we want it to tell us what's the weight on the picture. Let's code this. Okay, and it's as simple as that. Let's now use it. To use it, we'll need to give it a picture. For this, I prepared a little something. This is what I have prepared. It's very simple. Let's walk through it. It's going to be quick. So first thing, we will load a library called attachments. The attachments library is a library I made, and this is particularly good to give attachments, to give things to LLM. My mission with this library is to have this kind of general kind of funnel of anything to LLM. And so we'll use that because it gives us the opportunity to just in one line load files and images that are ready to give the LLM. We are here using the OS so that we can load the list of files that are in that directory. We are preparing an empty list. And so what we will do is that we're listing the file in that directory. We will only keep 3 because we don't need to process for so long. We'll wait too long for opening too many images otherwise. We are then iterating through these 3 files. And so here we are just reconstructing the path where we have the directory that is this, the file that is what the directory has read. We are then only saving that into the array here. We'll be printing it so we can see it. And I'll also display one of the image so we know what we're working with. That's it. And so we now have 3 attachments in our list, and they are HEIC, and we have a little bit of information too that will be given as text to the LLM to help it. And so here you can see that it's just like the label from a meat package, and it was for our lamb that we processed here on the farm. And what we want to know is this weight here, okay? And so we are going to simply give our attachments and one of them to our program. Because remember, we defined it as you take a picture, you give us weight and do chain of thought. That should be enough. Oh, we have to say that it's a picture. So off it goes. And there it is. So it has captured the weight as we wanted, just like that. Did some reasoning, and that's it. And that's all we needed in 3 code chunks. I don't know, maybe something like 10 lines of code. And now we are able to automatically extract weight from pictures. This is, I mean, I don't know any way we could have specified all of that shorter than this. It's very, very great. Okay, so this was our second program. Very, very simple program. We will start to complexify this program, okay, so that we learn other parts of signatures. And so we will start diving into signatures right now. What we can do here is that we can specify the type. You can see here, it gave it as a string because it also included the units here. So first thing you can do with a signature, if you want to have more control, go into more details, is that you can say what type you wanted out of it. So if we do that now, we will have a little bit of a different program, because now the program will be returning its output in float. And dspy will do the extraction and ensure that this is what we get. And so So we can see here that it has worked. Okay. If we ask for something that it cannot do, if we ask for an int, it will either kind of break or it will be creative, like here right now it has changed the unit to be able to give it to us like that. Okay. And remember, right now we're using GPT 4.1 Nano. We're using like a small cheap model, and it you know, we don't need to do any prompt engineering here. We're just defining our program and it works. Okay, so the best way will be a float. Now maybe I want to give it more instructions. If I want to give it a little bit more, I will be defining an inline signature, and then I can use instructions. Here you can see I gave it a little bit more details using instructions, and I had to call the signatures directly instead of just using the string. Now we will go the last step. So there are kind of three possible depths of defining your signatures. And the first one is the inline, just a small string. And then you can add the name of the inputs, the name of the outputs. You can put the file type. Second one, you can add instructions using signatures like that. Third one, we create it as a class. We can give a name to our class. So we'll take class weight. And so here what we will be defining, they are our inputs and our outputs. But in this case, we'll do equal dspy dot input field, and our outputs, let's go for the weight. We will give this straight into here, delete that. This is the other way we can define a signature. We define our inputs, define our outputs as a class, and then we give it to the modules that we want. In this case, we want chain of thought, but we could use predict. Let's change it like that. And we can run this, and here it is. We just have our response. Notice how we are back to string here because we didn't specify the type of our output. So we can do just the same as we were doing before, and see now we're back to floats. One thing I can do, if I want to give instructions, I can define the doc string here. So I can say extract weight, and these will be used as the instructions. If I print this, we can see a little bit more what this is about. And so we can see here that it's our simple signature with the arrow. We can see it has put the instructions here. We can see picture is a field, and there are no specific description. Weights is here. The last element we can add to our signature, there are descriptions for each field. And so we could say like meet label picture, and we can say weight found on label. You have to say description here. As we have seen, they are not necessary, and you shouldn't specify them if they are not necessary, because we managed to get our results when we had a briefer signature. So you always want to define your spec with the minimum amount of information you need to be very clear and not more. So now we have really seen everything there is to see about signature. Behind the scenes, the signatures are turned into prompts, and those prompts, they can be optimized. So far, we have not optimized any prompts, but you have seen that we always got the results we wanted, even if we were using GPT 4.1 Nano, a very, very small model. In the next section of this video, we will go check out how we can optimize our prompt. So for optimizing our prompt, we will use a situation where we will use a big model that will create a synthetic training set. And so we will believe that our big model will be smart enough to do the complete task perfectly. And what we will do is that we will optimize a prompt to find a way that a very small model can perform like the big model. And so then if we have to run that program on many items, it will cost us a lot less. But this is what we are going to move into right now. First thing, we'll be loading more libraries. In this case, we will load data-r. This is very similar to dpy-r, but in Python, for those who know. For those who do not know dpy-r, you're missing out. And lucky for you, I will teach you about data-r very, very quickly. The reason we will need another library here, it's that because we will be doing optimization, we need a training set. And for me, for my brain, or for what I'm used to do, the best way to hold a training set is a data frame. So I will do it like that. There are some tools in dspy to do that. They're not my favorite part of dspy. Not that it's particularly bad, it's just that data frames are already a complete world on their own, and so I'll pick from that world instead. We will want to install data, and I do it like this here. Python environment is a huge mess. If you find that difficult, you're not alone. Do not worry. The whole world finds it hard. One day we'll fix it. Now we have all our libraries. This will bring some nice functions that exist in R. This will be a helper to make the syntax similar to dplyr possible. This table here is table will be our object for holding data frame, and these are data transformation tools that exist in dplyr that we will be using. Just like before, we are configuring dspy, and in this case we will use Flash Lite from Gemini. Very, very cheap small model. Next step, we're already ready to create our dspy signature. So class count AI occurrences, dspy signature. We are going to set our inputs, so maybe to help us remember inputs, outputs. The inputs to that program will be paragraphs, and in this case we'll fetch a Wikipedia article using attachments. We'll split it up and into paragraphs with attachments, and then we'll give it to the program, each paragraph at a time. And what we will do is that we will ask it to find all of the terms that are related to AI and to count them. I had already made this tutorial in the written form on X, and I had a few comments where they were saying like, oh, it's really bad that you're using AI to count things where we could just use computers. But I disagree, because here I'm not counting words and exact things that we could do regex or we could do like exact match. I am counting something that is related to a fuzzy concept, the fuzzy concept of being related to AI. And what I want to do is to leverage the capacity of a SOTA model, like Sonnet 4 in this case, to delineate what is AI related and what does it mean. I have more trust that it will find that in a better way than myself, because it just read the whole internet, so it has this kind of fuzzy understanding of what this term means. Okay, so paragraphs, we'll give it as a string, and we describe it a little bit. So it's the paragraph that we have to count the AI mentions that are in it. We'll also give it some instructions because I want to be clear about that element of fuzzy concept I was telling you about. I need to say that here. Count the number of times the word artificial intelligence or AI or any other reference to AI or AI related terms appear in the paragraph. Okay, so those will be the instructions. And then output, just AI occurrences. I want this to be an integer. If I set it to a float, it's very interesting because it will start to give not complete points to some words. So they will be like, that's related, but it's not 100% related. Next, we put that signature around into a module, and I will actually use chain of thought here. In the program, I want it to be cheap, so I'll use predict, but to create it, I'll use chain of thought so that the SOTA model doing the training set has the best possible performance because we're spending some thinking time token. Yep. So let's just be explicit actually here. We are now ready to go get our data and put them into a table and to apply those programs. To get the online data, we will use attachments. And so attachments has a DSL so that you can give some options in the strings. But basically, the idea of attachments is that you give it a list of strings or many strings, and the mission of attachments is to know how to deal with it and transform that into LLM ready context. We will go fetch data from the artificial intelligence Wikipedia link, but we don't want the images, and in this case it's not fetching the images from the website that are on the website. It's actually taking a full screenshot of the website using Playwright. We will select elements from it. So we don't want all of the HTML stuff and everything. We just want information like the text, and we don't want the URLs and all those little pieces. So we just want the paragraphs, the title, and the headers. And we want to split that into paragraphs. And so we take all of that string of domain-specific language that we have here, and we make that longer. And then A will have everything we need. Time to create the data frame. To do this, we get our table and we create a column of paragraphs, and we pick the paragraphs from the attachments. We'll take only the first 20, and we grab the text from those because we don't need the images and there are no images. Then, like in dpy-ai, we have a pipe. So a pipe means that we will take all of the results from that and we'll give it as the first element here. And so mutate will do something on its first element, which is a data frame. And this is what it will do. And so what it will do is that it will add the column Flash response, so the response from Flash. And it will be something that we apply a function to our paragraphs, and each of them one after the other. This has to only be able to take one input because it will take this as input, and it has to not need arguments. So for this, we need to wrap these up a little bit into a function form. So we create this function, and basically it's that we get the paragraph, we pass it to the paragraph where we can specify that it's equal to the paragraph because the dspy module asks for that. And in this case, it will be the P version because we are doing for Flash. And we have to grab our output because we also need to receive only one output because this will be a value that we set to this column. And we're ready to go. And we're not because I just added the P here. So at this point, because of this function, which is calling the module on the paragraphs, now we're calling Flash lite on every element of the paragraph, and we're saving the result in that data frame. And so we'll display this data frame, and we have finished. And so we can see the paragraphs here, and we can see the value of the number of AI-related terms that Flash lite thought there were. Next, we will create the goal set because Flash lite will basically serve as our baseline. This is a non-optimized Flash lite run where it's just using the default prompt that's constructed from dspy. Here we will use Claude Sonnet to be doing our goal set. Okay, so it's just the same. We will grab every paragraph element in this column and we apply this function where in this case it's the chain of thought that we want. And so Sonnet will do the thinking on the paragraph, choose how many AI related terms it thinks there are. This will be returned here. It will be saved into that column variable for that data frame. And just so that we can kind of track our progress here, I will save it into a variable of a new name. I'm not calling things properly. So, yeah, I didn't do the second version of this is the one place where, it's not perfect, the dspy syntax. And I actually had fun creating a simpler syntax that gives you this function for free. And I did it into a small library called Funny dspy. You can go check it out on GitHub, or you can try it. It's Funny dspy. Well, of course, if I rename it the same, it's not going to help anybody. In this particular case, I am not running in parallel. I am not using some of the tools that dspy gives us to run on kind of launch many query at once to Sonnet. I'm just running them one after the other, and there's chain of thought, and we have our results. So we see that Flash and Sonnet do not agree on many of the instances. Let's look at the performance that we have for our baseline. So again, this is just data manipulation on a data frame we will just, we take our data frame, we are looking for every element, comparing them. So is this an exact match with that? We're gonna have true and false, which when you sum them, they are turned into integers. And so then we will sum all of the trues and we will divide that by the number of rows and get performance as a percentage. So yeah, so now we want to transform our data frame into a list of examples. dspy-ai's optimizer expect a list of examples. So to create a list, we create our list. We have our list object to which we append, and in it we are setting examples. Our examples will have our paragraphs, and it will have our response from Sonnet. And we say that the input in our example are the paragraphs. And this is just the way that we can loop through those records, or this is how we transform our data frame into a training set. And last step is to define the metric that we actually have created here. So this rule of this has to be equal to that. So this is our metric, just are they equal? And drum roll, now this is all the code you need to optimize your prompt. This is very short and simple. So dspy is giving us a list of optimizers. In this case, we're using MiPro v2. You can look in the documentation for other ones. We have to give it a metric. So we'll give our metric, we just define our function, exact match. We also have to, in this case, set a teacher model, teacher settings. And this can be a little bit different for different optimizers on how you give it. Optimizers can sometimes have teachers in different ways. And so in this case, we set teacher settings. And we set it to Sonnet 4. So in this case, what it means is that Sonnet 4 will be the one that will be trying to compose prompts. It will compose different types of prompts, and it will try to find the optimal prompts. Now we define our optimizer, we save it into a variable, and we compile it. So optimizer, this here, .compile, and we give it our module. And so in this case, we don't want to use the one we wrapped in a function. We want to use the dspy module directly because that's what the dspy expects and handles. We want to use predict. We want to use the base form of this, the one that takes less token. That would be more the cheapest. And so we use this one, and we give it our training set in the train set parameter, which we created here. In the end, we will get an optimized module. So it will be this, but with optimal prompt. Yeah, it's asking me for permission to run. We'll just say requires permission to run false. In the notebook environment, there are these small glitches sometimes. We had a small bug. You have to be careful that these names here, so the ones that we're putting in the example, really fit with everywhere, because otherwise it's just not gonna work, obviously, but it's a little thing. So our best program here did not actually improve much, but we'll see on our complete metric. And yeah, it's finished. Next step is to wrap the optimized module that we just got into the same type of function so we can use it again, just like we were used to before. Then we'll use that program just to, as an example, let's say this is about deep neural network. So it says it's 0. It's debatable, but I would say that there are at least 1 or 3. The 3 could be the answer. If I say AI, then it is. So this is using our now optimized prompt and optimized example. Now we are just going to evaluate the result. And so here, this is simple dplyr pipeline or data pipeline. Let's walk through it. We are grabbing our data frame we had before. We will add a column using mutate, and that column will be the response from Flash optimized. So same mechanics here. We're picking up this function here and we're applying it on every paragraph of this data frame. Then we will take that plus whatever other columns there were already and compute 2 new columns, which will be the columns with true or false, sonnet equal to flash response, sonnet equal to flash optimized response. And then we will do the same as we did before, where we sum all of the true value and divide that by the number of rows times 100. Then we get our 2 results. And if we want to see how much we improved, we will do after minus before and all of that into final performance, where we now in final performance pick the only column and only row that there are, and we will get our final performance. And the results are we improved by 10%. And so the baseline, like there are 2 ways you can interpret that. Baseline was already good, or in this case, it was hard to improve. You would have to look at your results more to understand if you, in this case, if your goal set you believe was a true goal set or not, and so on and so forth. It's not that hard. dspy is very these optimizers tend to be very efficient, and they tend to be very robust to overfitting. So even 4, 10, 15 good examples are enough to do prompt optimization. And so you want to collect those examples. I could have gone and I could have done, measured the number of AI words in a few paragraphs, and that may have been enough as a training set. It's like teaching by example, basically. We, as humans, also like to learn by examples. We go straight to the examples when we are learning to code. Like here, I'm basically showing you examples on how you can do things. It's just the same here. This is what it does. And so this concludes our tutorial on the simplest way to call LLMs and build programs on top of LLMs with LLMs in Python. dspy is really the best tool to do that right now. I really encourage you to take a look at it. And as you saw, it was very simple. With only these 5 lines of code here, you can go from nothing to call many different LLMs. Then with only these here, you can program, do a whole program, a whole RAG. And then afterwards, I showed you here how you can do an extraction of weights. And then we went through the whole pipeline to do evaluation and optimization. I hope you enjoy. See you next time.